6 billion years ago, when Earth was still a molten hellscape, something was born in the frozen darkness of another star system. It drifted. It waited. And now, after a journey longer than the existence of complex life on Earth, it's here, hurtling toward our Sun at 80,000 miles per hour. You're looking at 3I/Atlas, an interstellar comet wrapped in carbon monoxide, a chemical signature so rare it tells us this visitor formed in conditions nothing like our solar system. It survived the void between stars. It survived gravitational chaos. But what's waiting for it now is something far more violent. In the coming weeks, 3I/Atlas will reach perihelion, the death zone. Temperatures will surge from -200 Celsius to +300. Its nucleus will explode into a 100,000 kilometer coma. Solar wind travelling at 1,000,000 miles per hour will rip plasma tails across millions of miles of space. And here's the thing, some comets don't make it out alive. They shatter, they evaporate, they die. This interstellar traveller has one chance to survive, and you're about to witness every moment of it. Look, if you're the kind of person who wants to understand what actually happens when the universe gets violent, not the Hollywood version, the real physics you're going to want to see where this goes, we're tracking 3I/Atlas through perihelion with real data, real science, and zero fluff. If that sounds like your kind of content, smash that like button and subscribe. Hit the bell, because this show doesn't have reruns. Let's start with what makes 3I/Atlas so profoundly different from anything else in our cosmic neighbourhood. When astronomers first spotted this visitor on September 13th, 2024 using the ATLAS survey system in Hawaii, they knew within days that something was off. The spectroscopic signature, the fingerprint of light this comet was emitting, didn't match the profile of the thousands of comets we've catalogued over centuries. It was carbon monoxide, not water ice. Not the dusty, rocky composition we're used to. Carbon monoxide. Now, why does that matter? Picture this in our solar system. Comets form in a specific temperature range. Water ice dominates because temperatures in the region where most comets are born, the Kuiper Belt and Oort cloud, hover around -200 Celsius. Cold. Yes, but not cold enough to keep carbon monoxide frozen in significant amounts. CO only stays solid below -205 Celsius. That's a narrow margin, but it's critical. It means 3I/Atlas didn't form where our comets form. It formed somewhere colder, somewhere darker, somewhere we'll never reach. Dr. Teddy Careta from Lowell Observatory, who led the early spectroscopic analysis. Put it bluntly, this is a comet that tells us about a star system with fundamentally different chemistry than ours. It's like meeting someone who breathes a different atmosphere. And he's right. The carbon monoxide dominance suggests 3I/Atlas originated in the outer reaches of its home system, potentially beyond the equivalent of Neptune's orbit, in regions where sunlight was so faint that even volatile gases like CO could condense and stick together. Let's put this in perspective. Remember 1I/Oumuamua, the first confirmed interstellar object, spotted in 2017 that sent the scientific community into overdrive. We barely got a glimpse of it. It tumbled through our solar system so fast, travelling at 54 miles per second, that by the time we realised what it was already leaving. We learned almost nothing about its composition. Then came 2I/Borisov in 2019. That one was easier. It looked like a comet, behaved like a comet, and its water ice composition was comfortingly familiar. It could have been one of ours, but 3I/Atlas. It's a completely different beast. Its nucleus, the solid, frozen core at the centre of all that gas and dust, is estimated to be roughly 3 to 5 kilometres across. That's small by comet standards. Halley's comet, for comparison, is about 11 kilometers long, but size isn't what makes 3I/Atlas fascinating. It's the chemistry. According to data collected by the Gemini North Telescope and the European Southern Observatory's Very Large Telescope in Chile, the CO to dust ratio in 3I/Atlas is off the charts. We're talking about a comet where carbon monoxide outgasses at rates 10 to 20 times higher than the typical water-dominated comets in our system. Here's where it gets wild. Carbon monoxide is incredibly volatile. It doesn't need much heat to turn from ice into gas. At minus 205 Celsius, it sublimates, goes directly from solid to gas without melting. Water ice. You need to warm it up to around minus 100 Celsius before it starts doing the same thing. That means as 3I/Atlas approached the Sun over the past few months, it started waking up earlier and more violently than a water ice comet would. By the time it crossed the orbit of Mars in late 2024, its coma, the cloud of gas surrounding the nucleus, was already expanding rapidly. And this is where the story gets even more intense. On September 27, 2024, amateur astronomer José de Queiroz in Brazil noticed something strange while monitoring 3I/Atlas. The comet's brightness had suddenly spiked. Not gradually, not over weeks. In less than 48 hours, it brightened by more than half a magnitude visible to the naked eye under dark skies. Then it happened again on October 18th. Another outburst, another surge in brightness. These weren't gentle releases of gas. These were explosive events. Subsurface pockets of carbon monoxide ice, heated by the sun, building pressure until they erupted like grenades beneath the surface. Think about what that means for a moment. This object travelled through interstellar space for possibly millions of years. It survived temperatures just a few degrees above absolute zero. It dodged gravitational perturbations from rogue planets, close encounters with other stars, bombardment by cosmic rays. And now, as it closes in on our Sun, it's literally exploding. Not from external impacts, from internal pressure. Dr. Quanzi Ye, an astronomer at the University of Maryland who specializes in interstellar objects, described it this way in a November 2024 interview with Nature. We're watching a comet essentially self-destruct in slow motion. Every outburst is a sign that its structure is weakening. The question isn't whether it will fragment, the question is when? So what do we actually know for certain about 3I/Atlas right now? Let's break it down. Its orbital trajectory was confirmed in October 2024 by NASA's JPL Horizon system. It's on a hyperbolic orbit, meaning it's not bound to our Sun. It came from interstellar space, and it's going back. Its perihelion, the closest point to the Sun, is calculated at 0.3 astronomical units. That's 45 million kilometers. For reference, Mercury orbits at 0.39 AU, so 3I/Atlas is going to get closer to the Sun than the innermost planet in our system, and it's going to do that sometime in early March 2025. The closing speed roughly 80,000 miles per hour relative to the Sun. At that velocity, 3I/Atlas is covering the distance from Earth to the Moon in just about 3 hours. It's not slowing down, it's accelerating. And every day, the Sun's radiation gets more intense. Now here's what makes this moment so rare. We've only confirmed 3 interstellar objects in human history. 3 out of potentially billions passing through our solar system over millennia. We've spotted exactly 3. And of those 3, 3I/Atlas is the only one we're catching at its most active phase. Oumuamua was already leaving when we found it. Borisov gave us a decent show, but it stayed relatively calm. 3I/Atlas is exploding, brightening and evolving right in front of our telescopes. So when you hear astronomers say this is once-in-a-lifetime event, they're not exaggerating. The next interstellar comet could arrive next year, or never again in our lifetimes. There's no pattern, no schedule, just random chance and the vastness of space. But we're not just passively watching this visitor pass by, because what's about to happen as 3I/Atlas reaches perihelion isn't just a spectacle. It's a collision between an alien object and the most violent environment in our solar system. And when that collision happens, the physics gets brutal. So let's talk about what perihelion actually means when you're a frozen block of carbon monoxide and dust travelling at 80,000 miles per hour toward a nuclear furnace. Because this isn't just a close flyby. This is the equivalent of diving into a blast furnace while moving at the speed of a rifle bullet. Imagine you're 3I/Atlas right now. For the past several months, you've been coasting through the relatively calm outer solar system. Temperatures have been brutal -200°C, but stable. The sun is just a bright star in the distance, barely warming your surface. But as you cross the orbit of Mars, something changes. The sunlight intensifies, not gradually, exponentially. Every million kilometers you travel inward, the solar radiation hitting your surface quadruples. By the time you reach 0.3 AU 45 million kilometers from the sun, the temperature on your sunlit side will surge past 300 degrees Celsius. That's a 500-degree swing in a matter of weeks. Now, why does 0? 3 AU matter specifically, let's put this in context. Mercury, the closest planet to the sun, orbits at an average distance of 0.39 AU. At that distance, surface temperatures hit 430 degrees Celsius during the day. But Mercury is a solid rock with no atmosphere. It can take the punishment. 3I/Atlas is a loose collection of ice, dust, and frozen gases held together by weak gravitational forces. At 0.3 AU, it's going to experience conditions even more extreme than Mercury's day side. And unlike Mercury, which has had 4.5 billion years to bake under the sun's glare, 3I/Atlas has never experienced anything remotely like this. Here's where the physics gets vicious. Solar radiation doesn't just heat the surface, it penetrates. Infrared light from the sun drives thermal waves centimeters, even meters, into the comet's nucleus. Subsurface ice that's been frozen solid for billions of years suddenly finds itself warming up. Carbon monoxide ice. Remember, sublimates at -205 Celsius. But the surface of 3I/Atlas at perihelion will be more than 500 degrees hotter than that. The result: rapid, violent outgassing, gas pressure builds beneath the surface. Cracks form, and when the pressure exceeds the structural strength of the ice, entire sections of the surface can blow off in explosive jets. You want a real-world example of how destructive this process can be? Look at Comet Ison. In November 2013, Ison approached the Sun at a perihelion distance of just 0.012 AU, about 1.8 million kilometers. That's roughly 25 times closer than 3I/Atlas will get. Astronomers were calling it the comet of the century. Predictions suggested it would become one of the brightest comets in recorded history. Visible in broad daylight, instead it disintegrated. As Ison rounded the Sun on Thanksgiving Day 2013, NASA's Solar Dynamics Observatory and the SOHO spacecraft watched it happen in real time. The nucleus fractured. The coma dispersed. By the time Ison should have emerged from behind the Sun, there was nothing left but a faint dust cloud. Dr. Carl Battams from the Naval Research Laboratory, who tracked Ison's final moments, said it plainly: "We essentially watched a comet commit suicide. Now, 3I/Atlas isn't getting as close as Ison. Not even close." But here's the thing. Ison was a water ice comet. Water ice sublimates at -100 Celsius. Carbon monoxide sublimates at minus 205 Celsius. That means 3I/Atlas starts outgassing much earlier, much more violently, and under conditions where a water ice comet would still be dormant. So while 3I/Atlas has the advantage of staying farther from the Sun, it has the disadvantage of being chemically unstable in ways ISON never was. Let's talk about tidal forces, because they're just as dangerous as the heat. When an object gets close to a massive body like the Sun, gravity doesn't pull evenly. The side of the comet facing the Sun experiences stronger gravitational pull than the side facing away. This difference, called a tidal gradient, creates stress. For solid objects like planets, this stress is negligible, but for loosely bound rubble piles like comets, it can be catastrophic. There's a boundary called the Roche limit, and it defines the distance at which tidal forces will literally rip an object apart. For a comet orbiting the Sun, that limit is roughly 0.005 AU, about 750,000 kilometers. 3I/Atlas will pass at 0.3 AU 60 times farther than the Roche limit. So it's safe from tidal disruption. Right, not necessarily, because the Roche limit assumes a solid, cohesive object. Comets aren't solid. They're fractured, porous, and riddled with voids and weak zones. In 2020, Comet Atlas, C 2019Y4, no relation to our 3I/Atlas, just an unfortunate naming coincidence, began fragmenting while still 1.5 AU from the Sun. It wasn't tidal forces that killed it. It was structural weakness combined with thermal stress. Hubble images from April 2020 showed the nucleus breaking into more than 30 distinct fragments, each trailing its own mini-coma. The comet essentially fell apart under its own outgassing pressure. So what are 3I/Atlas's odds of survival? Dr. Matthew Knight at the US Naval Academy, who studies comet fragmentation, estimated in a December 2024 preprint that the survival probability depends almost entirely on the nucleus's tensile strength, how well the ice and dust are cemented together. If 3I/Atlas has a strong, consolidated nucleus, it'll make it through perihelion battered but intact. If it's a loose rubble pile, what scientists call a talps, or barely bound pile of debris, then every outburst weakens the structure. And at perihelion, when thermal stress peaks, the whole thing could come apart. Think about the stakes here. If 3I/Atlas survives, it becomes one of the best studied interstellar objects in history. We'll have spectroscopic data, thermal profiles, outburst patterns, and compositional analysis spanning months. If it fragments, we lose that opportunity, but we'd gain something else, a real-time view of an interstellar comet's internal structure. We'd see what it's made of, how it's layered, whether interstellar comets are fundamentally different from ours in construction, not just chemistry. And here's the kicker, we won't know which way this goes until it happens. The outbursts in September and October 2024 have already shown that 3I/Atlas is structurally stressed. Each eruption ejects tons of material into space, material that can never be recovered. The nucleus is getting lighter, weaker, more fragile. By the time it reaches perihelion in early March 2025, it will have endured months of thermal assault, dozens of outbursts, and gravitational stress from the Sun's immense pull. Some comets walk into this zone and walk out stronger, others don't walk out at all. The difference often comes down to minutes, one last outburst at exactly the wrong moment, one thermal crack propagating through a critical support structure, one pocket of volatile gas exploding at perihelion when the nucleus is already barely holding together. But before we get to that critical moment, before we see whether 3I/Atlas lives or dies, we need to understand what's already happening around it. Because right now, even before perihelion, this comet is transforming. Its frozen nucleus is waking up. And what's emerging is one of the most spectacular structures in the solar system, a coma that's growing larger than Jupiter. The transformation doesn't happen all at once. It starts small, a few molecules of carbon monoxide escaping from the surface. Then a few thousand, then millions. By the time 3I/Atlas crossed the orbit of Mars in late 2024, it was shedding roughly 200 kilograms of gas every second. That might not sound like much, it's about the weight of 2 average adults, but remember, we're talking about gas expanding into the vacuum of space. And in a vacuum, gas doesn't just drift away, it explodes outward at supersonic speeds. Here's what that looks like in practice. Carbon monoxide molecules on the surface of 3I/Atlas absorb sunlight. The energy breaks the molecular bonds holding the ice together. Suddenly, you've got free CO molecules with nowhere to go but up. They launch off the surface at speeds reaching 500 meters per second, that's 100 miles per hour. For perspective, that's faster than the speed of sound on Earth. These molecules collide with dust particles embedded in the ice, dragging them along. Within hours, what was once a frozen, dormant nucleus becomes the center of an expanding cloud of gas and dust. This cloud is the coma, and it grows fast. By early October 2024, amateur astronomers using backyard telescopes in Australia reported that 3I/Atlas's coma had already reached 50,000 kilometers in diameter. That's nearly 4 times the width of Earth. By mid-November, observations from the Lowell Observatory in Arizona measured the coma at 80,000 kilometers. And here's the wild part, it's not done growing. Dr. Michael Kelly at the University of Maryland, who studies cometary atmospheres, ran thermal models in late 2024 predicting that by the time 3I/Atlas reaches perihelion, its coma could expand to 150,000 kilometers or more. For context, Jupiter, the largest planet in our solar system, has a diameter of 140,000 kilometers. This interstellar visitor, with a nucleus barely 5 kilometers across, will be wrapped in a cloud larger than Jupiter. Now, why does the coma grow so dramatically? It's all about sublimation rates. The closer 3I/Atlas gets to the Sun, the more intense the solar radiation becomes. And more radiation means more energy driving sublimation. But here's where carbon monoxide's chemistry becomes critical. Water ice requires significant energy input to sublimate. It has a high latent heat of vaporization. Carbon monoxide much lower. It takes far less energy to turn CO ice into CO gas. So while a water ice comet might sublimate a few hundred kilograms per second at this distance, 3I/Atlas is already outgassing at rates typically seen much closer to the Sun. Let's break down the structure of this coma, because it's not just a random blob of gas. It's layered, organized, almost alive in the way it responds to sunlight. At the very center, you've got the nucleus, the tiny, solid core. Surrounding that is the inner coma, a dense region where gas and dust are so thick that molecules collide constantly. This region extends maybe 1000 to 5000 kilometers from the nucleus. Here, temperatures can reach 200 Kelvin, that's minus 73 Celsius. Still freezing by Earth standards, but warm enough that certain chemical reactions start happening. CO molecules can collide with dust grains, electrons can be stripped off atoms by solar ultraviolet light, creating ions beyond the inner coma. You've got the outer coma. This is where the gas has expanded enough that collisions become rare. Molecules are essentially in free flight, travelling ballistically away from the nucleus. The outer coma is where most of the visible light comes from. Not because the gas itself glows, but because sunlight reflects off the dust particles mixed in with the gas. Observations from the Gemini South Telescope in Chile in November 2024 showed that 3I/Atlas's outer coma has a distinct greenish tint. That colour comes from diatomic carbon C2 molecules fluorescing under solar UV radiation. It's the same process that makes certain minerals glow under a black light. But here's what makes 3I/Atlas's coma truly unusual. Its composition is asymmetric. Most comets have comas that expand relatively evenly in all directions, but spectroscopic data from the European Southern Observatory's Very Large Telescope reveal that 3I/Atlas's coma is lopsided. The side facing the Sun is denser, brighter, and more active than the side facing away. Why? Because the nucleus itself is rotating, and it's not rotating evenly. As the nucleus spins, different areas are exposed to sunlight at different times. Some regions are rich in carbon monoxide ice. These are the active zones that produce powerful jets. Other regions are covered in a dark, dusty crust that insulates the ice beneath. When an active zone rotates into sunlight, outgassing spikes. When a dusty zone faces the sun, outgassing drops. Dr. Tony Farnham at the University of Maryland, who analysed the rotation patterns from Hubble data, collected in October 2024, estimated that 3I/Atlas completes one full rotation every 7 to 9 hours. That's actually pretty fast for a comet. Halley's comet, for comparison, rotates once every 52 hours. The rapid spin means that jets of gas and dust are constantly turning on and off as active zones rotate in and out of sunlight from Earth. This creates a flickering effect. The comet brightens and dims on a regular cycle as jets fire and then shut down. Now imagine you're observing this from space. You'd see a small dark nucleus too small to resolve, with most telescopes surrounded by a vast, glowing halo, jets of gas streaming out from specific points on the surface, spiralling away as the nucleus rotates, dust particles reflecting sunlight, creating a fuzzy, diffuse glow, and all of this expanding outward at over 1000 miles per hour, faster than a speeding bullet. But the coma isn't static. It's constantly being reshaped by forces beyond the comet's control. Solar radiation pressure, the physical force exerted by photons from the sun, pushes dust particles away from the nucleus. The lighter the particle, the faster it's pushed. This creates a sorting effect. Heavy grains stay close to the nucleus, while fine dust gets swept outward, creating the glowing outer coma. And then there's the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, flowing out from the sun at speeds around 400 kilometers per second. That's nearly 1,000,000 miles per hour. It carries with it the sun's magnetic field, creating a dynamic, turbulent environment that extends throughout the entire solar system. And when the solar wind hits a comet's coma, things get violent. Here's the setup. The coma is full of neutral gas molecules: carbon monoxide, carbon dioxide, nitrogen, traces of water vapor. These molecules are uncharged. The solar wind, on the other hand, is a plasma, a soup of electrically charged particles. When solar UV light hits the neutral molecules in the coma, it ionizes them. An electron gets knocked off. Suddenly, you've got a positively charged ion drifting through the coma. And ions don't just drift. They respond to magnetic fields. The magnetic field embedded in the solar wind grabs these ions and accelerates them. The result, a glowing tail of ionized gas stretching millions of kilometers away from the nucleus, always pointing directly away from the sun. But we're getting ahead of ourselves. Because before we see that tail, before the solar wind carves a plasma streamer across millions of miles of space, there's a collision about to happen. The leading edge of 3I/Atlas's expanding coma is about to slam headfirst into the solar wind. And when that happens, the physics stops being gentle. It becomes a cosmic car crash at 1,000,000 miles per hour. Picture a supersonic jet breaking the sound barrier. The air in front of the jet can't get out of the way fast enough, so it piles up, compresses, and creates a shock wave, a sudden violent boundary where the physics changes in an instant. That's exactly what happens when 3I/Atlas's coma collides with the solar wind, except instead of air molecules, you've got ionized gas travelling at 400 kilometers per second. And instead of a jet, you've got an expanding cloud of carbon monoxide slamming into a hurricane of charged particles. This collision creates what's called a bow shock. It's one of the most dramatic boundaries in space physics, and it forms roughly 100,000 to 200,000 kilometers in front of the comet, about halfway to the moon if you scaled it to Earth distances. On one side of the bow, shock, you've got the pristine solar wind flowing smoothly outward from the sun. On the other side, chaos. The solar wind slams into the outer edge of the coma, decelerates violently, heats up, and gets deflected around the comet like water flowing around a rock in a stream. But this isn't water. This is plasma ionized gas where every particle carries an electric charge. And when plasma gets compressed and heated, it doesn't just warm up, it glows. The electrons in the plasma get excited to higher energy states, then drop back down, releasing photons. The result is a faint bluish emission that traces the shape of the bow shock. You can't see it with the naked eye, but ultraviolet telescopes like those on NASA's Solar Dynamics Observatory can pick it up. In fact, similar bow shocks have been observed around other active comets, including Comet Encke during its 2017 perihelion passage, where the shock extended more than 250,000 kilometers from the nucleus. Now here's where it gets interesting. The bow shock isn't smooth. It's turbulent, unstable, constantly rippling and reforming as the solar wind conditions change. The sun doesn't emit a steady stream of particles. It pulses. It fluctuates. Occasionally, it erupts. Coronal mass ejections, massive blobs of plasma and magnetic field hurled out from the sun can hit comets like tidal waves. When a CME passes over a comet, the solar wind density can increase by a factor of 10 or more in just a few hours. The bow shock compresses inward, the pressure on the coma spikes, and the entire structure can be temporarily disrupted. This happened to Comet Lovejoy in December 2011, as Lovejoy plunged toward the sun, reaching a perihelion of just 0.0055 AU. One of the closest approaches ever recorded, it flew directly through an active region of the solar corona. Multiple CMEs slammed into it over a span of 2 days. SOHO spacecraft images captured the moment when the bow shock collapsed entirely, and the solar wind carved directly into Lovejoy's inner coma. The comet survived, barely, but its tail was torn off and had to reform over the following days. Dr. Carol Shriver from Lockheed Martin Solar and Astrophysics Lab, who analysed the event, described it as watching a comet endure the equivalent of a cosmic sandblaster at point-blank range. 3I/Atlas won't get as close as Lovejoy, but it's going to experience similar physics, just at a slightly safer distance. And here's the thing, the solar wind isn't the only force acting on the coma. There's also radiation pressure. Photons from the sun, pure light, carry momentum. When a photon hits a dust particle, it transfers that momentum, pushing the particle away from the sun. This force is incredibly weak if you tried to use radiation pressure to push a car. You'd need the light output of 1,000 suns focused on it. But in the vacuum of space, acting on tiny dust grains over weeks and months, radiation pressure is powerful enough to shape entire comet tails. Here's how it works. Dust particles in the coma come in a range of sizes. The smallest submicron grains, maybe 1/10 of a micrometer across, are so light that radiation pressure accelerates them to high speeds almost instantly. Larger grains, a few micrometers across, get pushed more slowly. The result is a sorting process. Small grains race ahead, creating a diffuse, curving dust tail. Larger grains lag behind, staying closer to the nucleus. This creates a fan-shaped structure that curves gently away from the Sun, following the comet's orbital path. But the ion tail, the tail made of ionized gas, behaves completely differently. Ions don't respond to radiation pressure. They respond to magnetic fields, and the magnetic field embedded in the solar wind is constantly moving, twisting, reconnecting. When ions in the coma get picked up by this field, they're accelerated along magnetic field lines, typically straight away from the Sun. The result is a narrow, straight tail that can extend millions of kilometers into space. Now, how long can these tails get? Let's look at the record holders. The Great Comet of 1843 holds the all-time record. Its ion tail stretched an estimated 300 million kilometers, roughly twice the distance from the Earth to the Sun. From Earth, the tail spanned more than 60 degrees of sky, about the length of your fist held at arm's length 6 times over. More recently, Comet Hale-Bopp in 1997 developed a dual tail system, a blue ion tail and a white dust tail that remained visible to the naked eye for a record 18 months. At its peak, the ion tail extended 150 million kilometers. So what can we expect from 3I/Atlas early predictions from researchers at the Planetary Science Institute in Arizona? Based on outgassing rates observed in late 2024, suggests that the ion tail could reach lengths of 50 to 80 million kilometers by perihelion. That's roughly 1/3 the distance from Earth to the Sun. The dust tail will likely be shorter, maybe 10 to 20 million kilometers, but more visually prominent because dust reflects sunlight more efficiently than ionized gas. Here's something most people don't realize: comet tails don't always point away from the Sun. Well, they do, but not in the way you'd think. As a comet moves along its orbit, the tail drags slightly behind the direction of motion, creating what looks like a curved arc. But from certain viewing angles specifically, when Earth is aligned just right relative to the comet's orbit, you can see what's called an anti-tail. It's an optical illusion. You're actually looking along the plane of the comet's dust tail, and because of perspective, it appears to point toward the Sun instead of away from it. Comet Aaron Rowland in 1957 displayed a spectacular anti-tail that confused astronomers for weeks until they figured out the geometry. Will 3I/Atlas produce an anti-tail? Maybe. It depends on the orbital alignment during perihelion. But what's certain is that the tail system will evolve rapidly as the comet approaches the Sun. Every day, the solar wind will get denser. Every day, radiation pressure will intensify. And every day, more gas will ionize, more dust will be liberated, and the tails will grow longer, brighter, more dramatic. But here's what really sets 3I/Atlas apart from every other comet we've studied: the chemistry. Because while the tail structure follows the same physics as any other comet, the material being expelled is fundamentally different. This isn't water vapor and silicate dust. This is carbon monoxide, carbon dioxide, and hydrocarbon molecules from an alien star system. And that chemical signature is about to ignite in ways we've never seen before. Let's talk about what makes carbon monoxide so dangerous and so fascinating when it comes to comets. In our solar system, most comets are water ice bodies with some carbon dioxide mixed in. When you analyze their spectra, the fingerprint of light they emit, you see strong emission lines from hydroxyl radicals, cyanogen, and C2 molecules. These are the breakdown products of water and simple organic compounds. They're predictable. We've been studying them for decades. 3I/Atlas doesn't play by those rules. When spectroscopists at the Gemini Observatory aimed their instruments at this comet in October 2024, they saw something they weren't expecting. The dominant emission line wasn't hydroxyl. It wasn't cyanogen. It was carbon monoxide specifically. The CO molecule's rotational vibrational bands in the ultraviolet spectrum. The signal was so strong that it overshadowed nearly everything else. Dr. Alan Fitzsimmons from Queen's University Belfast, who co-authored the spectroscopic analysis published in November 2024, put it this way: "This is the most CO-rich comet we've ever observed. The ratio of carbon monoxide to water is at least 50 to 1, possibly higher. For context, in typical solar system comets, their ratio is closer to 1 to 10. So why does that matter? Because carbon monoxide is extremely volatile. Remember, it sublimates at minus 205 Celsius. Water ice doesn't sublimate until you reach minus 100 Celsius. That 105-degree difference means CO starts outgassing much earlier in a comet's approach to the Sun. But it also means something more profound. 3I/Atlas formed in a region of its home star system that was cold enough to trap carbon monoxide as ice. That's colder than the regions where even our outermost comets, those in the Oort cloud, originated. We're talking about formation temperatures potentially as low as minus 260 Celsius. That's just 13 degrees above absolute zero. What does that tell us? It tells us the star system 3I/Atlas came from at a protoplanetary disk, the disk of gas and dust that eventually forms planets with a very different temperature profile than ours. Either the star itself was cooler than our Sun, producing less heat, or 3I/Atlas formed in the extreme outer regions of its system, far beyond where even Neptune-like planets would have formed. Dr. Darrell Seligman from Cornell University, a leading researcher on interstellar objects, suggested in a December 2024 paper that 3I/Atlas may have originated in the outer disk of a red dwarf star system, stars much cooler and dimmer than the Sun, where the snow line for carbon monoxide could exist as close as 20 to 30 AU. But the carbon monoxide isn't just sitting passively in the nucleus, it's actively driving the outbursts we've been seeing. Here's the mechanism as 3I/Atlas moves closer to the Sun. Solar radiation penetrates the surface and begins warming subsurface ice, carbon monoxide ice, being so volatile, starts sublimating even when the surface is still well below freezing. Gas pressure builds in pockets beneath the surface, voids and cracks in the nucleus where CO gas accumulates. Eventually, the pressure exceeds the structural strength of the overlying ice. The surface ruptures, gas explodes outward at supersonic speeds, dragging dust and debris with it. This is an outburst, and 3I/Atlas has been experiencing these outbursts regularly. The first major event happened on September 27, 2024. Amateur astronomer Michael Jaeger in Austria, who's been photographing comets for over 30 years, captured images showing the comet's brightness had increased by more than half a magnitude, roughly 60% brighter, in less than 48 hours. Then it happened again on October 18th. Another surge. Another explosion of material. By mid-November, astronomers were detecting smaller outbursts almost weekly, each one releasing an estimated 10 to 50 tons of carbon monoxide gas in a matter of hours. What's driving this pattern rotation? As the nucleus spins, completing one rotation every 7 to 9 hours, different areas are exposed to sunlight. Active zones rich in CO ice rotate into daylight, heat up rapidly, and trigger outbursts. Then, as that zone rotates back into shadow, the outgassing shuts down, but the next active zone is already rotating toward the Sun, ready to explode. Dr. Dennis Bodowitz from Auburn University, who specializes in cometary volatiles, described this in a November 2024 webinar. It's like a rotisserie chicken, except instead of browning evenly, certain spots are catching fire and shooting jets of gas into space. Now, compare this to water ice comets. Comet 67P/Churyumov-Gerasimenko, famously visited by the European Space Agency's Rosetta mission from 2014 to 2016, displayed similar jet activity but driven by water sublimation, not carbon monoxide. Rosetta observed that 67P's jets turned on and off as the nucleus rotated, with active zones producing plumes of water vapor and dust. But the process was relatively gentle. Outgassing rates increased gradually as 67P approached perihelion. There were no explosive outbursts. The nucleus remained stable throughout. 3I/Atlas is behaving far more violently, and there's a reason for that. Carbon monoxide's latent heat of vaporization is much lower than water's. In simpler terms, it takes less energy to turn CO ice into CO gas, so when subsurface CO ice starts sublimating, it does so rapidly, building pressure fast. Water ice, on the other hand, requires more energy input and sublimates more slowly, allowing gas to escape gradually through pores and cracks. The result, water ice comets tend to be more stable. CO-rich comets tend to be explosive. Here's where things get even more interesting. Carbon monoxide isn't the only volatile in 3I/Atlas. Spectroscopic observations from the Very Large Telescope in Chile detected traces of carbon dioxide CO2, molecular nitrogen N2, and even methane CH4. These are all extremely volatile compounds, more so than water. They form at different temperatures, meaning 3I/Atlas's nucleus is likely layered. Outer layers might be richer in CO and CO2, while deeper layers could contain methane and nitrogen ice. As the nucleus heats up and layers of ice sublimate away, we're essentially peeling an onion. Each layer reveals new chemistry, and here's the kicker: some of these volatiles are reactive. When carbon monoxide molecules in the coma are hit by solar ultraviolet light, they can break apart, forming atomic carbon and oxygen. These atoms can then recombine with other molecules, creating new compounds that don't exist in the nucleus. For example, atomic carbon can combine with leftover CO molecules to form C2 diatomic carbon, which produces the greenish glow we see in the outer coma. Atomic oxygen can strip electrons from other molecules, creating ions that get swept into the ion tail. The coma becomes a chemical factory, constantly producing new molecules through photochemistry. Dr. Anita Cochran from the University of Texas, who analysed the spectral evolution of 3I/Atlas from September to November 2024, noted that the CN to C2 ratio, a standard diagnostic in comet chemistry, was abnormally low. In typical comets, you see comparable amounts of both molecules, but in 3I/Atlas, C2 dominates, while CN is barely detectable. Cochran's interpretation: this suggests that the parent molecules producing CN, likely hydrogen cyanide or cyanogen, are either depleted or simply weren't present in significant quantities when the comet formed. That's consistent with an origin in a very cold, carbon-rich environment where nitrogen chemistry was suppressed. Think about what this means for the bigger picture. We're not just studying a comet, we're studying the chemical composition of another star system's building blocks. Every molecule we detect, every ratio we measure, tells us something about the conditions in that distant protoplanetary disk 6 billion years ago. Was nitrogen abundant? Was water present? Were organic molecules forming? These are the same questions we ask about the early solar system, and now we're getting answers from a completely different stellar environment. But as spectacular as the chemistry is, it's also dangerous. Because carbon monoxide isn't just volatile, it's energetic. And as 3I/Atlas continues its dive toward perihelion, those subsurface pockets of CO ice are heating up faster than ever. The outbursts are becoming more frequent, more powerful. And at some point, one of those outbursts might be strong enough to crack the nucleus wide open. When an outburst happens, it's not just gas escaping, it's an explosion. And when you're dealing with a nucleus that's already structurally compromised, riddled with voids, cracks, and weak zones, repeated explosions can be catastrophic. Every outburst weakens the integrity of the ice, Every ton of material ejected means less mass holding the nucleus together. And at perihelion, when thermal stress is at its peak and outgassing rates are at their maximum, the entire structure could fail. This is what happened to Comet 73P/Schwassmann-Wachmann 3 in 2006. It wasn't an interstellar visitor, it was a Jupiter family comet, orbiting the Sun every 5.4 years, but in 1995, during a particularly intense perihelion passage, it began fragmenting. By 2006, the nucleus had split into more than 60 distinct pieces, each one trailing its own coma and tail. Hubble captured stunning images showing fragments labelled alphabetically: Fragment B, Fragment C, Fragment G, spread across millions of kilometres of space. Some fragments survived, others disintegrated completely within weeks. Dr. Hal Weaver from Johns Hopkins Applied Physics Laboratory, who led the Hubble observations, described the fragmentation as a cascade failure. Once the first crack propagates through the nucleus, it creates new surfaces that are suddenly exposed to sunlight. Those surfaces start outgassing. That creates new stresses. More cracks form. It's a runaway process. The key question for 3I/Atlas is whether it's already in the early stages of that cascade, or whether it's structurally robust enough to withstand the punishment. Let's look at the evidence. The outbursts in September and October 2024 were significant, but they didn't result in visible fragmentation. If the nucleus had cracked apart, we'd expect to see multiple brightening centers in high-resolution images, distinct cores, each with its own small coma. Observations from the Las Cumbres Observatory Global Telescope Network in November 2024 showed no such structure. The coma remained centrally concentrated, suggesting the nucleus was still intact. That's a good sign. But it's not a guarantee. Here's the problem: we don't actually know what 3I/Atelis's nucleus looks like up close. Is it a single monolithic block of ice? Or is it a rubble pile, a loosely bound collection of smaller chunks held together by weak gravitational forces and frozen volatiles acting as glue? Most comets are thought to be rubble piles. Observations of Comet NP/Temple, one which NASA's Deep Impact mission deliberately crashed a probe into in 2005, revealed that the nucleus was porous, fragile, and held together by surprisingly weak forces. The impact created a crater, but it also released far more material than expected, suggesting the interior was riddled with voids and cavities. If 3I/Atlas is similarly structured, then every outburst is like setting off a small bomb inside a house of cards. Eventually, the structure gives way. But if it's more consolidated, if the ice is compacted, sintered, and tightly bound, then it might survive even the most violent outgassing events. We won't know for sure until perihelion. Now, let's talk about what happens during an outburst at the level of individual gas molecules, because the physics here is genuinely wild. Imagine you're a CO molecule trapped in the subsurface ice. You're surrounded by other CO molecules, all locked in a crystalline lattice at -200 Celsius. Then, suddenly, solar radiation penetrates through meters of ice and starts warming your region. The temperature climbs -210, -208, -206, and then you hit -205, the sublimation point. The lattice structure breaks. You're free. But there's a problem: you're surrounded by millions of other molecules that just became free at the same instant. There's nowhere to go. Pressure builds, and then the ice above you fractures. You're accelerated through the crack at 500 meters per second, faster than the speed of sound. This process releases enormous amounts of energy. When ice sublimates, it absorbs latent heat from its surroundings. This is why evaporating sweat cools your skin. But in an outburst, the sublimation happens so rapidly that it creates a localized cooling zone around the vent. Surface temperatures near active jets can actually drop by 50 degrees or more, even as the surrounding areas heat up. This creates thermal gradient stress zones where hot and cold regions meet, and thermal stress, combined with outgassing pressure, is one of the leading causes of cometary fragmentation. We saw this exact mechanism in action with Comet 17P/Holmes in October 2007. Holmes was a faint, unremarkable comet until it suddenly brightened by a factor of 1 million in less than 24 hours. 1 million. It went from magnitude 17 visible only through powerful telescopes to magnitude 2.8 easily visible to the naked eye. What caused it? A massive subsurface outburst. Models suggest that a cavity filled with volatile ices, possibly carbon monoxide, heated up, built pressure, and then exploded, blowing off a huge section of the nucleus's outer layers. The event released an estimated 100 million tons of dust into space. Holmes survived, but barely. Its nucleus was permanently altered, and it's never displayed the same level of activity since. Could 3I/Atlas experience a Holmes-type event? Absolutely. The conditions are similar: a CO-rich nucleus, subsurface volatile pockets, increasing solar heating. The September and October outbursts may have been small precursors, test runs, if you will. As the comet gets closer to the Sun, the frequency and intensity of these events will only increase. By the time 3I/Atlas reaches perihelion in early March 2025, it could be experiencing multiple outbursts per day, possibly even per rotation cycle. Dr. Matthew Knight from the Naval Research Laboratory, who's been tracking 3I/Atlas's brightness since its discovery, ran probabilistic models in December 2024 to estimate fragmentation risk. His team's conclusion: there's roughly a 30 to 40% chance of at least partial fragmentation at perihelion. That's not a certainty, but it's not negligible either. For context, when Comet Ison approached the Sun in 2013, similar models gave it a 20% fragmentation probability, and Ison disintegrated completely. Here's what makes 3I/Atlas's situation uniquely precarious. It's not just fighting thermal stress and outgassing pressure, it's also battling rotational stress. Remember, the nucleus is spinning once every 7 to 9 hours. That's a relatively fast rotation for a comet. Centrifugal forces, the outward pulling sensation you feel on the spinning carnival ride, act on every part of the nucleus. For a loose rubble pile, centrifugal force can overcome the weak gravitational and cohesive forces holding it together. There's a critical rotation rate called the spin barrier, and if a comet spins faster than that, it flies apart. Comet 2019 LD2, discovered in June 2019, provided a dramatic example. Initially classified as an asteroid, it was later reclassified as a comet when it developed a faint coma. But in November 2020, observations showed it had split into at least 2 pieces. Follow-up analysis revealed the cause: the nucleus had been spinning so fast once every 4 hours that centrifugal forces literally pulled it apart. No thermal stress, no outburst, just pure rotational breakup. 3I/Atlas is spinning slower than the critical rate models suggest. The spin barrier for an object its size is around 1 rotation every 3 to 4 hours, so it's safe from rotational disintegration under normal conditions. But here's the catch: every outburst changes the rotation rate. Gas jets act like rocket thrusters. If a jet fires preferentially from one side of the nucleus, it creates torque, speeding up or slowing down the spin. Over weeks and months, repeated outbursts can alter the rotation period significantly. If the spin accelerates too much, the nucleus could cross the spin barrier and then it's game over. So as we watch 3I/Atlas barrel toward perihelion, we're essentially watching a structural endurance test. Can the nucleus hold together under thermal stress? Outgassing pressure, rotational forces, and tidal effects Or will one final outburst, one last explosion at exactly the wrong moment, shatter it into fragments? The stakes are enormous. If 3I/Atlas survives intact, it becomes one of the most valuable interstellar objects ever studied. But if it fragments, we don't lose the science, we gain something entirely different. We get to see inside an interstellar comet. We get to analyse its internal structure, its layering, its composition at depth. Either outcome teaches us something profound about where this visitor came from and how it survived its journey across the stars. But fragmentation isn't just a scientific curiosity, it's a death sentence. And when it happens fast. Let's walk through what fragmentation actually looks like in real time, because the physics here is as brutal as it is fascinating. First, understand that a comet nucleus isn't held together by much. There's gravity, but for an object only 3 to 5 kilometers across. Gravitational binding is incredibly weak. The escape velocity from 3I/Atlas's surface is probably around 2 to 3 meters per second. That's walking speed. If you could stand on the nucleus and jump, you'd float off into space. So what's really holding it together? Tensile strength. The mechanical bonds between ice grains, dust particles, and frozen volatiles. Think of it like a snowball. Compress it in your hands and it holds its shape. But throw it against a wall and it shatters. Now imagine that snowball is spinning, heating up, and exploding from the inside. That's 3I/Atlas at perihelion. When fragmentation begins, it often starts with a single crack. Maybe it's a pre-existing fault line, a structural weakness dating back to the comet's formation. Maybe it's a fresh fracture caused by thermal stress or an outburst. Either way, once a crack forms, it propagates rapidly. Cracks in ice can travel at speeds of several hundred meters per second. Within minutes, a crack can split the entire nucleus in half. What happens next depends on how the nucleus breaks. If it splits cleanly into 2 large pieces, those pieces may initially stay close together, orbiting each other in a slow, gravitational dance. This is what happened to Comet Biela in the 19th century. Discovered in 1826, Biela returned in 1846, but instead of one comet, observers saw 2 orbiting each other at a distance of about 240,000 kilometers. The pair returned again in 1852, now separated by nearly 2 million kilometers. By 1872, Biela had vanished entirely, likely disintegrated into a meteor stream. But for a few decades, it existed as a binary comet system. More often, though a fragmentation is catastrophic, the nucleus doesn't split cleanly, it shatters. Dozens, sometimes hundreds of fragments fly apart, each one tumbling chaotically. Some fragments are large enough to continue outgassing, developing their own miniature comas. Others are just inert chunks of ice and rock, destined to fade into obscurity. This is what happened to Comet Linear in 2000. Discovered in February, Linear brightened rapidly as it approached the Sun. But by late July, something went wrong. Images from the University of Hawaii show the nucleus breaking into at least a dozen fragments. By August, those fragments had themselves fragmented. By September, Linear was gone, reduced to a faint, diffuse cloud of dust with no discernible nucleus. Dr. Zdenek Zekanina from NASA's Jet Propulsion Laboratory, who analysed Linear's demise, noted that the fragmentation cascade happened over just 6 weeks. He described the process as a structural avalanche. Once the nucleus lost its mechanical integrity, every subsequent outburst accelerated the breakup. Fragment sizes range from several hundred meters down to centimeters. Most of the smaller fragments sublimated completely within days. So, if 3I/Atlas fragments, what will we see initially? A sudden brightening, Fragmentation exposes fresh ice to sunlight ice that was previously buried beneath insulating layers. That ice sublimates rapidly, releasing gas and dust. The comet's brightness can increase by a factor of 10 or more in just a few hours. Observers on Earth would see the coma expand, becoming more diffuse. The central condensation, the bright core where the nucleus resides, would blur, spreading out as fragments separate. Within days, high-resolution telescopes like Hubble would start resolving individual fragments. Each fragment would appear as a tiny point of light, each one surrounded by its own faint coma. The fragments would spread out along the comet's orbital path, forming a linear chain. This debris train can stretch for thousands, even millions of kilometers. Comet Shoemaker-Levy 9, which famously collided with Jupiter in 1994, existed as a chain of 21 fragments spread across 1.1 million kilometers a distance, nearly 3 times that between the Earth and the Moon. But here's the thing, not all fragments survive. Smaller pieces, those less than a few hundred meters across, lose mass so rapidly through sublimation that they can disintegrate entirely within weeks. Larger fragments, a kilometer or more across, have enough mass and insulating material to survive longer. They become mini comets in their own right, each one following a slightly different trajectory as solar radiation pressure and outgassing jets nudge them onto diverging paths. Now, what about tidal forces? We talked earlier about the Roche limit, the distance at which tidal forces tear an object apart. For 3I/Atlas, that limit is around 0.005 AU, or 750,000 kilometers from the Sun. At its perihelion distance of 0.3 AU, 45 million kilometers, tidal forces are far too weak to directly disrupt the nucleus, but they can exacerbate existing weaknesses. If the nucleus has already developed cracks from thermal stress or outbursts, tidal forces can pry those cracks open wider. It's like pulling on the 2 halves of a broken bone. You're not causing the break, but you're making it worse. We've seen this before with sun-grazing comets that pass extremely close to the Sun, often within the Roche limit. Comet Lovejoy in 2011 survived a perihelion passage of just 0.0055 AU, skimming through the Sun's corona at temperatures exceeding 1,000,000 degrees. But most sun grazers don't survive. The SOHO spacecraft, which monitors the Sun continuously, has observed more than 4,000 comets plunging toward the Sun since 1996. The vast majority, over 85%, disintegrate completely, either from tidal disruption, thermal vaporization, or both. 3I/Atlas isn't a sun grazer. It's staying far enough away that tidal disruption shouldn't be a primary concern. But combine tidal stress with thermal stress, outgassing pressure, rotational forces, and structural weaknesses, and you've got a recipe for disaster. So here's the critical question: what determines whether a comet survives perihelion or fragments doctor? Nalin Samarasina from the Planetary Science Institute, who spent decades studying cometary fragmentation, points to 3 key factors. First, tensile strength. How well bonded is the ice? Is it pristine? Consolidated ice or loose? Porous rubble. Second, thermal conductivity. How quickly does heat penetrate the nucleus? Low conductivity means heat stays near the surface, creating steep thermal gradients and high stress. High conductivity means heat spreads evenly, reducing stress. Third, volatile distribution. Are volatiles concentrated in pockets, creating localized pressure zones, or are they distributed uniformly, allowing gas to escape gradually? For 3I/Atlas, we can make educated guesses, but we don't have definitive answers. The outbursts suggest volatiles are concentrated in pockets. Bad news for structural stability. The rapid brightness variations suggest the nucleus is heterogeneous, with active zones and inactive zones. Also bad news. But the fact that it survived this long enduring multiple outbursts without fragmenting, suggests it has at least moderate tensile strength. That's encouraging. Think of it this way, 3I/Atlas has already been through a lot. It survived ejection from its home star system, a process that likely involved gravitational perturbations from a giant planet or close encounter with another star. It survived millions of years in interstellar space, enduring cosmic ray bombardment and impacts from interstellar dust grains travelling at hundreds of kilometers per second. It survived entering our solar system, passing through the heliopause, the boundary where the solar wind meets the interstellar medium, a region of turbulent plasma and shock waves. And now it's surviving the intense radiation environment of the inner solar system. But perihelion is different. Perihelion is the ultimate test. It's the moment when every structural weakness, every thermal gradient, every pocket of volatile ice is pushed to the breaking point. And for 3I/Atlas, that moment is approaching rapidly. Yet even if fragmentation happens, even if the nucleus shatters into a dozen pieces, there's still something beautiful to witness. Because those fragments won't just disappear, they'll continue their journey, each one a small reminder of the comet that was. And together, they'll create one of the most spectacular shows in the solar system, a display of light, gas, and dust stretching across millions of kilometers of space. That spectacle, the tail system, is where physics becomes art. Because a comet's tail isn't just a single structure, it's a complex dynamic system involving two completely different types of tails, each one governed by different physics, each one telling a different story about what's happening at the nucleus. Let's start with the ion tail, because it's the most dramatic. Ion tails are made of plasma ionized gas where electrons have been stripped away, leaving positively charged molecules. These ions are created when solar ultraviolet light hits neutral gas molecules in the coma. A photon with enough energy, typically in the extreme ultraviolet range, around 10 to 100 nanometers wavelength, smacks into a carbon monoxide molecule and knocks an electron loose. What you're left with is CO+, a carbon monoxide ion with a positive charge. Now, here's where it gets interesting. Charged particles respond to magnetic fields, and the solar wind, remember, carries the sun's magnetic field with it as it streams outward. When a CO+ ion drifts into this magnetic field, it gets captured. The field lines act like rails, accelerating the ion to incredible speeds, 300 to 500 kilometers per second. That's more than 1,000,000 miles per hour. Within hours, ions that were created near the nucleus are millions of kilometers away, stretched into a narrow, straight tail that always points directly away from the sun. Ion tails glow blue, not because the ions themselves are blue, but because of fluorescence. When sunlight hits CO+ ions, they absorb ultraviolet light and re-emit it at specific wavelengths in the blue part of the spectrum, around 420 nanometers. The same thing happens with ionized water molecules H2O+ and carbon dioxide ions CO2+. Though their emission wavelengths differ slightly, the result is a ghostly blue streamer extending across the sky, visible even from Earth under dark conditions. Comet Hyakutake in 1996 produced one of the most spectacular ion tails ever recorded. At its peak in late March 1996, the tail stretched more than 500 million kilometers, over 3 times the distance from Earth to the Sun. From Earth, it spanned 80 degrees of sky, nearly half the visible dome overhead. Observers in rural areas with dark skies reported being able to see structure in the tail kinks, waves, disconnection events where portions of the tail broke off and drifted away. Dr. John Brandt from the University of New Mexico, who studied Hyakutake's tail dynamics, noted that the tail was so long that the far end was experiencing solar wind conditions completely different from those near the nucleus. Now, the dust tail, completely different beast. Dust tails are made of solid particles, tiny grains of silicate, carbonaceous material, and organic compounds lifted off the nucleus by outgassing. These particles don't respond to magnetic fields, they're electrically neutral. Instead, they respond to two forces: solar radiation pressure and gravity. Solar radiation pressure is subtle but relentless. Photons from the sun carry momentum. When a photon hits a dust grain and gets absorbed or reflected, it transfers that momentum to the grain, pushing it away from the sun. The smaller the grain, the stronger the effect. A submicron grain 1/10 of a micrometer across experiences radiation pressure strong enough to accelerate it to several hundred meters per second within days. Larger grains, a few micrometers across, accelerate more slowly. The result is a sorting process. Small grains race ahead, forming the outer, more diffuse regions of the dust tail. Large grains lag behind, staying closer to the nucleus. But dust particles also feel gravity specifically, the sun's gravity. While radiation pressure pushes them away, gravity pulls them inward, curving their trajectory. The balance between these two forces determines the shape of the dust tail. For very small grains, radiation pressure dominates, and the particles shoot almost straight back. For larger grains, gravity bends the trajectory into a broad, curving arc. The result is a fan-shaped tail that sweeps back along the comet's orbital path. Dust tails glow white or yellowish because they reflect sunlight, unlike ion tails, which emit their own light through fluorescence. Dust tails are purely reflective. You're seeing sunlight bouncing off trillions of tiny mirrors, and because dust particles scatter light in all directions, dust tails are often much brighter and more visually prominent than ion tails, even though they're not physically longer. The Great Comet of 1861 is a perfect example. Its dust tail was reported to stretch 120 degrees across the sky. That's 2/3 of the visible hemisphere. Observers in Europe and North America described it as a luminous sword hanging over the horizon, bright enough to cast faint shadows at night. The tail was so bright that people could read newspapers by its light in rural areas, yet the ion tail, though present, was barely visible to the naked eye. So what can we expect from 3I/Atlas based on the carbon monoxide-rich composition? The ion tail will likely dominate. CO molecules ionize efficiently under solar UV radiation, and CO plus ions are lightweight, meaning they accelerate quickly in the solar wind. Early predictions from modeling teams at NASA's Goddard Space Flight Center suggest the ion tail could reach 50 to 100 million kilometers by perihelion. That's roughly 1/3 to 2/3 the Earth-Sun distance. From this is Earth, depending on viewing geometry. That could translate to a tail spanning 10 to 20 degrees of sky, about the width of your fist held at arm's length. The dust tail will be shorter but more visually striking. Observations from the Spitzer Space Telescope's successor instruments, designed to detect infrared emissions from warm dust, could reveal dust particles extending 10 to 20 million kilometers behind the nucleus. These particles, heated by sunlight to temperatures around 200 to 300 Kelvin, will glow faintly in the thermal infrared, creating a heat map of the dust distribution. Now, here's something most people don't realize: comet tails are not stable structures. They're constantly being disrupted, torn apart and reformed by changes in the solar wind. When a coronal mass ejection from the sun hits a comet, the sudden increase in solar wind density and magnetic field strength can cause what's called a disconnection event. The ion tail literally gets severed from the coma. The disconnected section drifts away, carried by the solar wind, while a new tail begins forming near the nucleus. This happened to Comet Encke in April 2007, as Encke rounded the sun at a perihelion distance of 33 AU. A CME slammed into it. Images from NASA's stereo spacecraft captured the moment of impact the ion tail, which had been stretching steadily behind the comet. suddenly detached within hours. The severed tail had drifted millions of kilometers away, and a new, fainter tail was growing in its place. Dr. Geraint Jones from University College London, who analysed the stereo data, described it as watching the comet's tail get guillotined in real time. Could 3i/Atlas experience a disconnection event? Almost certainly. The Sun is currently in an active phase of its 11-year solar cycle. With frequent CMEs and high-speed solar wind streams, between now and perihelion, 3i/Atlas will likely encounter multiple CME impacts. Each one could trigger a disconnection, creating a series of detached tail segments drifting through space ghost tails, marking the comet's path like breadcrumbs. And then there's the anti-tail phenomenon. Remember, comet tails always point away from the Sun, but from certain viewing angles, perspective can create an optical illusion where a portion of the dust tail appears to point toward the Sun. This happens when Earth passes through the plane of the comet's orbit. You're looking edge-on at a flat fan-shaped dust tail. The far edge of the tail, millions of kilometers away, appears to be in front of the nucleus because of perspective. It's the same illusion that makes railroad tracks appear to converge in the distance. Comet and Rowland in April 1957 displayed the most famous anti-tail in history. For several nights, observers reported a bright spike extending forward from the nucleus, seemingly defying physics. Astronomers were baffled until they worked out the geometry. Earth had crossed the orbital plane, creating the perfect viewing angle for an anti-tail illusion. The spike wasn't real, it was just a trick of perspective. Will 3i/Atlas produce an anti-tail? Maybe. It depends on the orbital alignment at perihelion. But whether we see one or not, the dual-tail system blue ion tail, white dust tail will be unmistakable. Together, they create a cosmic signpost, pointing not just away from the Sun, but toward the comet's origins in the frozen darkness of another star system. But the tails aren't just beautiful, they're functional. They're broadcasting a signal to every telescope on Earth and in space. A signal packed with data about the comet's composition, its outgassing history, its interaction with the solar environment. And right now, dozens of telescopes are pointed at 3i/Atlas, recording every photon, every spectral line, every subtle change in brightness and colour. Because this is where the real science happens. This is where 3i/Atlas transforms from a beautiful spectacle into a goldmine of data that's rewriting our understanding of interstellar chemistry, planetary system formation, and the fundamental building blocks of worlds beyond our own. Let's start with the ground-based observatories, because they're the first line of defense. Within days of 3i/Atlas's discovery in September 2024, astronomers at more than 40 observatories across 6 continents began pointing their instruments at this visitor. The Atlas survey telescopes in Hawaii, the same system that discovered it, continued daily monitoring. The Las Cumbres Observatory Network, a globally distributed fleet of robotic telescopes, allocated observation time every clear night. In Chile, the Gemini South Telescope and the Very Large Telescope began spectroscopic campaigns, breaking down the comet's light into its component wavelengths to identify which molecules were present. Spectroscopy is the key here. When you look at sunlight reflected off 3i/Atlas, you're not just seeing white light, you're seeing a spectrum, a rainbow of colours, each one corresponding to a specific wavelength. But embedded in that spectrum are dark lines. Absorption features where specific molecules in the coma have absorbed light at characteristic wavelengths. Carbon monoxide absorbs at 154 nanometers. Water vapor absorbs at multiple wavelengths in the infrared. Cyanogen CN molecules absorbs at 388 nanometers. By measuring the strength of these absorption lines, Astronomers can determine not just what's in the coma, but how much of it there is. Dr. Michael DeSanti from NASA's Goddard Space Flight Center, who's been conducting infrared spectroscopy of 3I/Atlas using the iShell spectrograph at NASA's Infrared Telescope facility in Hawaii, reported in November 2024 that the CO to H2O ratio was off the charts. His team measured a ratio exceeding 100:1, meaning for every water molecule in the coma. There were more than 100 carbon monoxide molecules. For context, in typical solar system comets, that ratio is closer to 1:5. DeSanti's conclusion: we're looking at a comet that formed in an environment fundamentally colder and more carbon-rich than anything in our system. But ground-based telescopes have limitations. Earth's atmosphere absorbs most ultraviolet and infrared light, blocking critical wavelengths where many cometary molecules emit. That's where space-based observatories come in. Hubble Space Telescope, which, despite being more than 30 years old, remains one of the most powerful tools for studying comets. Its ultraviolet spectrographs can detect molecules that are completely invisible from the ground. In October 2024, Hubble observed 3I/Atlas for a total of 12 orbits, about 18 hours of observation time capturing high-resolution images and spectra of the inner coma. What did Hubble see for one? It confirmed that the nucleus is still intact, no signs of fragmentation as of mid-November. But more importantly, it detected emission from atomic oxygen and carbon in the inner coma, signature products of CO photodissociation. When ultraviolet light from the sun hits a CO molecule, it can break the bond between carbon and oxygen, creating two free atoms. These atoms then emit light at specific wavelengths: oxygen at 130 nanometers, carbon at 165 nanometers. By measuring these emissions, Hubble's instruments can estimate how rapidly CO is being destroyed in the coma, a key parameter for understanding the comet's lifetime. Then there's the James Webb Space Telescope. Webb, with its massive 6.5-meter mirror and infrared sensitivity, is uniquely suited to study cold objects like comets. In late November 2024, Webb conducted a director's discretionary time observation of 3I/Atlas, a high-priority science target that bypasses the normal proposal process. Webb's near-infrared spectrograph captured data in the 1 to 5 micrometer range, a wavelength regime where carbon monoxide, carbon dioxide, and methane all have strong absorption features. Early results, presented at the American Geophysical Union meeting in December 2024, revealed something unexpected. Trace amounts of methanol, CH3OH, and formaldehyde H2CO in the coma. These are organic molecules, complex compounds containing carbon, hydrogen, and oxygen. Their presence suggests that 3I/Atlas's parent star system had active organic chemistry, possibly even the precursors to amino acids and other prebiotic molecules. Dr. Stephanie Millam from NASA Goddard, who led the Webb observations, described it as a chemical snapshot of another solar system's building blocks molecules that might have seeded life on planets we'll never see. But telescopes can only tell us so much. They give us composition, brightness, tail structure. What they can't give us is detailed spatial information about the nucleus itself. For that, you need close-up imaging, and that's where spacecraft come in, or would, if we had one. Here's the frustrating reality. We don't have a spacecraft at 3I/Atlas. There's no probe orbiting it, no lander on its surface, no impactor smashing into it to reveal its interior. When Oumuamua passed through in 2017, we weren't ready. By the time we realized it was interstellar, it was already leaving. When Borisov arrived in 2019, there were discussions about a rapid response mission launching a small spacecraft to intercept it, but the mission never got funded. The logistics were too challenging, the timeline too short. 3I/Atlas is different. We've known about it since September 2024. Perihelion isn't until March 2025. That's 6 months enough time, theoretically, to launch a mission. But spacecraft don't work that way. Even the fastest missions, New Horizons to Pluto, Parker Solar Probe to the Sun, took years of planning, design and testing before launch. You can't just throw together a mission in 6 months, no matter how important the target, so we're observing from a distance. And yet, despite the lack of a dedicated spacecraft, we're learning more about 3I/Atlas than we learned about either Oumuamua or Borisov. Why? Because we're catching it at the right time. Oumuamua was already leaving when we found it. We only had a few weeks of observations before it became too faint to detect. Borisov gave us longer, but it remained relatively inactive, never approaching close enough to the Sun to produce dramatic outbursts. 3I/Atlas is giving us the full show outbursts. Coma expansion, tail development, and soon, perihelion passage. And the data is pouring in, not just from professional observatories, but from amateur astronomers around the world. The global amateur astronomy community has become an essential part of modern cometary science. Amateurs with backyard telescopes often costing less than a decent used car are contributing nightly images, brightness measurements, and tail morphology observations. These observations, aggregated through platforms like the Comet Observation Database (COBS), provide continuous monitoring that even professional observatories can't match. Take José de Queiroz, the Brazilian amateur who first noticed the September outburst. His observation triggered follow-up by professional telescopes, leading to spectroscopic confirmation of the event within 48 hours. Or Michael Jaeger in Austria, whose high-resolution images in October revealed fine structure in the coma jets and streamers that weren't visible in lower-resolution professional images. These aren't just hobbyists. They're citizen scientists making real contributions to our understanding of this object. But here's the deeper question. Why does 3I/Atlas matter? Why are we devoting so much telescope time, so much computational power, so much human effort to studying a single comet? Because this isn't just about one object, it's about understanding the diversity of planetary systems across the galaxy. Every molecule we detect, every ratio we measure, every structural detail we observe is a piece of a larger puzzle. How do other star systems form? How do their chemistries differ from ours? What does that tell us about the conditions necessary for planets and life to emerge? 3I/Atlas is a messenger. It's carrying information encoded in its ice, its dust, its molecular composition, information about a star system we'll never visit, planets we'll never see, chemistry that unfolded billions of years ago in a region of space so far away that light from it hasn't even reached us yet, and in a few short months after perihelion, 3I/Atlas will leave. It will accelerate outward, fading from view, eventually exiting the solar system entirely and returning to the interstellar void. But before it does, before it disappears forever, we're going to extract every last photon of data we can, because this opportunity, this window into another star system's history, won't come again anytime soon, and what we learn might reshape our understanding of how worlds are born. So let's talk about what happens after the drama, after the outbursts, after perihelion, because for 3I/Atlas, March 2025 isn't the end of the story, it's just the beginning of the final chapter. Imagine this, it's early March 2025. 3I/Atlas has just rounded the Sun at 0.3 AU, surviving the closest approach. Whether it emerged intact or fragmented, is now accelerating outward, climbing back up the gravity well of the inner solar system. The intense heating is over. Surface temperatures are dropping, but the comet is still active. In fact, for several weeks after perihelion, it might be more active than it was going in. This seems counterintuitive. Right. You'd think once the comet starts moving away from the Sun, activity would decrease immediately, but that's not how it works. Comets often display what's called post-perihelion brightening, a surge in activity weeks or even months after perihelion. The reason is thermal lag. The nucleus doesn't heat up and cool down instantly. It's like a pot of water on a stove. When you turn off the heat, the water doesn't cool immediately. It takes time for the thermal energy to dissipate. For 3I/Atlas. Subsurface ice that was heated during perihelion continues to sublimate even as the comet moves away from the Sun. Heat that penetrated meters into the nucleus during the close approach is now driving out gassing from layers that were previously dormant. The result continued, sometimes even increased, activity for weeks after perihelion. Comet Hale-Bopp displayed this behavior dramatically in 1997. Its peak brightness didn't occur at perihelion on April 1st, but rather 2 weeks later, on April 14th, when post-perihelion outgassing reached maximum intensity. So let's project forward. By late March 2025, 3I/Atlas will be around 0.5 AU from the Sun, roughly the orbital distance of Mercury. Still close, still hot. The coma will remain large, though beginning to shrink as outgassing rates decline. The ion tail, that glowing blue streamer, will still stretch millions of kilometers into space, though growing fainter as fewer ions are being produced. And the nucleus, assuming it survived, will finally begin to cool down. By April, 3I/Atlas will cross Earth's orbit, though Earth itself will be nowhere near the crossing point. The comet will be roughly 1 AU from the Sun, the same distance as Earth, but in a completely different part of the solar system. At this distance, surface temperatures will have dropped to around -50 Celsius. Carbon monoxide sublimation will slow dramatically. The outbursts will stop. The coma will begin to fade. Here's where things get interesting from an observational standpoint. As 3I/Atlas moves outward, it's getting farther from Earth. By mid-2025, it will be 2 to 3 AU away, twice to 3 times the Earth-Sun distance. Its brightness will drop accordingly. The inverse square law is brutal: double the distance, and brightness decreases by a factor of 4. By June 2025, 3I/Atlas will likely fade below naked eye visibility, requiring binoculars or small telescopes to see. By August, only larger amateur telescopes and professional observatories will be able to track it. But astronomers won't stop watching, because this is when we get to see the comet's true nature. The post-perihelion phase is critical for understanding long-term evolution. How quickly does the activity shut down? Does the nucleus develop an insulating crust of dust and refractory material substances that don't sublimate, that seals in the remaining volatiles? Or does outgassing continue, gradually? For months or even years, Comet Hyakutake provides a cautionary tale. After its spectacular 1996 apparition, it was expected to return in about 70,000 years. But detailed orbital analysis revealed that its close pass by Earth and the Sun had altered its trajectory. Outgassing jets, those rocket-like forces from sublimating ice, had nudged it onto a slightly different path. The new orbital period, over 100,000 years. Outgassing, even at low level, can have long-term dynamical consequences. For 3I/Atlas, the situation is more extreme. It's on a hyperbolic orbit. It's not coming back, ever, as it moves outward, crossing the orbits of Mars, then Jupiter, then Saturn. It will continue to accelerate, not because of its own propulsion, but because the Sun's gravity is releasing its grip. By late 2025, 3I/Atlas will be moving at around 30 kilometers per second relative to the Sun. That's 67,000 miles per hour. Fast enough to escape the solar system entirely. Let's map out the timeline. By January 2026, 3I/Atlas will be around 5 AU from the Sun, somewhere between Jupiter and Saturn. At this distance, temperatures will have plummeted to -200°C, the same temperature it experienced when it first entered the inner solar system. The coma will have collapsed. The nucleus will be dormant, frozen solid once again. It will look like an asteroid, a dark, inert rock drifting through space. But it won't be an asteroid. It will still be a comet, just sleeping, waiting. If you could somehow transport it back to the inner solar system, it would wake up again. The carbon monoxide ice would sublimate. The coma would reform. The tails would grow, but that won't happen. 3I/Atlas is heading outward, and nothing will bring it back. By 2027 or 2028, it will cross the orbit of Uranus. By the early 2030s, Neptune. And by the 2040s, it will reach the Kuiper Belt, the region of icy bodies beyond Neptune where many of our own comets originate. But 3I/Atlas won't linger. It will pass through the Kuiper Belt like a bullet through fog, barely slowing down. Sometime in the 2050s or 2060s, it will cross the heliopause, the boundary where the solar wind gives way to the interstellar medium. This is the edge of the solar system, roughly 120 AU from the Sun. Voyager 1 crossed this boundary in 2012 after 35 years of travel. 3I/Atlas will make the journey in a fraction of that time, thanks to its higher velocity. And once it crosses the heliopause, it will officially return to interstellar space. What happens then? Nothing dramatic. No explosion. No transformation. It will just drift for thousands of years, millions of years, billions of years. The sun will shrink to a bright star in the sky, then fade to just another point of light. Eventually, 3I/Atlas will be so far away that the sun will be indistinguishable from the other stars in the galaxy. It will be alone again, as it was before it entered our system. But here's the haunting part. 3I/Atlas will carry with it a record of its visit. Every gram of ice it lost, every molecule it shed, every fragment that broke off all of that material is now part of the solar system. The carbon monoxide molecules that escaped at perihelion are mixing with the solar wind, dispersing across interplanetary space. The dust particles ejected from the nucleus are drifting on their own trajectories. Some of them might eventually be captured by planets or moons, in a very real sense. 3I/Atlas left a piece of another star system here, scattered across our cosmic neighbourhood, and we're taking something from it too. Not physically, we didn't send a spacecraft to collect samples, but we've captured its light, we've recorded its spectrum, we've measured its composition. Every observation, every data point, every image is now stored in archives on Earth. Future scientists, decades or centuries from now, will be able to revisit this data, analyze it with new techniques, draw new conclusions. 3I/Atlas will live on in our databases long after it's vanished from our telescopes. Dr. Michelle Bannister from the University of Canterbury in New Zealand, who studies interstellar objects, reflected on this in a December 2024 interview. Every interstellar visitor is a time capsule. They carry information about stellar environments we can't reach. 3I/Atlas told us about carbon-rich, cold disk chemistry. The next visitor might tell us something completely different. But we only get these stories if we're watching, if we're ready. And that's the question, isn't it? When will the next interstellar visitor arrive? We don't know. Statistically, we should detect 1 or 2 per year with current survey capabilities. But Oumuamua was 2017. Borisov was 2019. 3